Today, we're going to trace the incredible journey of computing. We're going to see how we went from a machine that could only do one thing at a time to this global network that lets millions of us stream movies, search for information, and connect with each other, all at the same time. We're going from one to many.
So let's start with something we all pretty much take for granted. You hit play on that new movie on Netflix, simple, right? But what you might not think about is that millions of other people are doing the exact same thing at the exact same moment. So how on earth does the whole system not just buckle under the pressure? Well, the answer is a fascinating story about evolution, from one to many.
To really understand how we got to this massive global scale, we've got to rewind. We have to go all the way back to the beginning, to how computers first thought about problems, one single thing at a time. Welcome to the one-lane highway of computing.
This is what we call serial computing. And the analogy on the slide nails it. It's like a grocery store with only one cashier open. Every single task, every customer has to get in line and be processed one after another. Sure, it's simple, it's methodical, but you can probably guess what happens when things get busy. That line gets super long and everything just grinds to a halt.
So, how do you solve the one cashier problem? Well, it's obvious, right? You open more checkout lanes. And that is exactly what computing did next. It was time for a power-up.
And this brings us to parallel computing. Instead of having one processor chugging through a giant long list of instructions, the idea is to break that big problem into a bunch of smaller, bite-sized pieces. Then you get multiple processors, our new cashiers, to work on all those little pieces at the same time, all inside the same computer.
And honestly, the difference is just night and day. Serial computing is one task, one processor, one at a time. Parallel computing is many tasks spread across many processors all happening at once. For really huge jobs like weather forecasting or complex scientific simulations, this was an absolute game changer, a massive leap in speed.
Now, this powerful new way of thinking needed some specialized gear. And the funny thing is, the absolute perfect tool for the job, well, it wasn't cooked up in some high-tech science lab. It was actually being built for video games.
And here it is, the GPU, the Graphics Processing Unit. Now, its original job was pretty specific, render the millions of pixels that make up the images you see in video games. But then, some really smart engineers had this aha moment. They realized its design, which is packed with thousands of tiny little cores, was perfect for any big task you could split into thousands of smaller parallel jobs.
The best way to picture this is the brain versus muscle analogy. The CPU is the brain. It's the manager. It's fantastic at complex, step-by-step logic and telling everyone what to do. The GPU? That's the muscle. It's a huge team of workers ready to tackle thousands of simple, repetitive tasks all at once. And you know what? This brain and muscle combo is exactly why GPUs became the engine behind the whole modern AI revolution.
Okay, so parallel computing made a single computer incredibly powerful. But even the beefiest supercomputer in the world has its limits. If you want to serve the entire planet, you have to think even bigger. You've got to connect them all.
And that brings us to the next level, distributed computing. Our analogy gets another major upgrade here. We went from one cashier to a whole supermarket with lots of cashiers, and now we're talking about an entire chain of supermarkets, spread all across the globe, all working together. Each computer is its own store, but they all collaborate over a network to handle a massive number of customers.
So let's circle back to our Netflix question. How does it really work? When you press play, your request doesn't travel across the world to some single giant Netflix computer. No way. Instead, a super smart system instantly routes your request to a server that is physically close to you and one that has enough juice to stream the movie right now. That is distributed computing in action, happening millions of times every single minute.
But this brings up a new, pretty important question. I mean, with thousands of computers all working together, something is bound to break, right? What happens then? Does the whole thing just fall apart?
The answer is this really beautiful concept called fault tolerance. See, these systems are literally designed with failure in mind. They expect it. Your data, your tasks, they're copied and spread across many different machines. So if one server goes down, another one just instantly takes its place without missing a beat. And for you, the user, the service just keeps working. You never even have a clue that a problem was just solved.
Building a global system that can handle failure is an incredible feat. But, keeping it from total chaos requires a set of very clever rules to manage all the work and all the data that's flying around.
The first rule is load balancing. You can't just let all the user requests flood a single server while other servers are just sitting there twiddling their thumbs. A load balancer acts like a traffic cop, intelligently directing incoming work to the servers that are least busy. This keeps everything running fast and prevents any one machine from getting totally overwhelmed.
But that traffic cop leads to an even trickier problem. I mean, think about it. If you update your profile picture in New York, how does a server in Tokyo know about that change instantly? How do you make sure that every computer all over the world agrees on what the correct data is at the exact same moment? This is a huge challenge.
And the solution is this brilliant compromise called eventual consistency. See, trying to force every single server in the world to be perfectly in sync every millisecond would be incredibly slow and fragile. So instead, the system guarantees that eventually, and we're talking like a few seconds maybe, all the servers will agree on the correct data. That tiny, almost unnoticeable delay is the small price we pay for a global system that's incredibly fast and almost never goes down.
So let's just put it all together. We journeyed from the raw simplicity of serial computing to the incredible speed of parallel processing happening on one machine, and finally to the global scale and rock-solid reliability of distributed systems. Each step built on the last, creating the powerful computing world we live in today.
And that brings us to today. We've effectively built a single, planet-spanning computer out of millions of individual machines all working in concert. The foundation has been laid. So the only question that's really left is, what incredible challenges are we going to solve with it next? Thanks for joining me.